So this is our first lecture in Thermo 2. It covers the topic Introduction to Exergy. This term, Exergy, looks a lot like another term that you spent a lot of time studying in Thermo 1. It's one letter off from that other term. What is the other term? Energy. And the letter off is just now they put an X instead of an N. Do you think that was by design, or do you think that was an unfortunate coincidence that both terms, energy and exergy, are so close in spelling? Do you think it was by design they chose it that way, or by accident? It's by design. This term is very, very, very closely linked to energy. Well, you studied energy, right? What is energy? Ability to do work. Person just gave me the most beautiful definition of exergy. Yeah. So if you look at our thermo book, and what's the topic of study in our thermodynamics textbook? Energy, its various forms, and the transformation of energy between forms, and the limitation on the transformation of energy between forms. And we have some very useful forms, the things that we like. We like power, able to lift things, push things, accelerate things. And then where we get a lot of energy from, combustion, burning things, making things hot. But energy was never defined. Look for the definition. Look for the very one or two sentence definition of energy in your thermodynamics textbook. Who would like to do that for me? Professor, we spent the whole semester studying thermodynamics, and the foundational concept of thermodynamics is energy, and the author of the textbook failed to define energy? You got to be joking me. No, that's not right. Structure has to be wrong. Go look for it, please. It's worth your time to look for it. And then when somebody asks you, oh, you studied thermodynamics, what's it all about? And you give the answer, well, energy is the ability to do work. Energy. What exactly is it if it's not the ability to do work? Actually, exergy is the ability to do work. Then what is energy? It's not defined. But if I ask a question, I think if you go out and look, you'll get a more vague answer, because energy is a vaguer, larger concept than just exergy. Okay, but energy is really the ability to have an effect. That's about it. So if you have a lot of energy, you're going to have a lot of effect. Okay? All right. So we're going to be able to talk about the exergy of a system, and then we'll do an exergy balance for a closed system. We'll talk about a slightly different exergy for an open system where you have fluid flowing in and out. You know what? That's where we were introduced to H in our energy balance. We had U, and then all of a sudden, pop, in Thermo 1, we start talking about H. Did U and H have the same units? Yeah. Oh, that was very confusing in Thermo 1. Internal energy and enthalpy have the exact same units, but they're not exactly the same property. One is used for a closed system analysis where flow is not going across the border or boundary of a control volume. One is used if the flow is going across the boundary of a control volume, if we have an open system analysis. We're going to do the same thing. We're going to have exergy for studying closed systems, then we'll have an exergy for flow exergy, or for studying open systems. And then we'll talk about exergetic efficiencies, but that's getting too far. You can Google this. Just say define exergy. Isn't that? This is my new dictionary. This is my new encyclopedia. I don't have to have the books on the shelf. I just say define the term, and it comes up typically with a pretty good definition. So exergy is the energy that is available to be used. It's the useful energy. A lot of times they used to call it the availability. But then they thought, availability? No, it's a more confusing term. They coined exergy. Exergy is a more popular term, although you'll still see people use availability as a term. It's a property of the system, and it's a property of the measure of the energy that can be converted to be useful to do work. So after the system and the surroundings reach equilibrium, the exergy is zero. That's another concept, another sentence. So right away, if the system is in equilibrium with the environment, the surroundings, there's no pressure difference, there's no temperature difference, you can't, as a clever engineer, get any work out of the system. Its exergy is zero. All right, the next concept, determining exergy, was also the first goal of thermodynamics. Even though we spend all the time talking about energy, it really was when they started off studying thermodynamics, they said, how much, if I burn this amount of coal, how much work can I do? How much water can I lift, and how high can I lift it? That type of. So it was really the concept of converting energy into the most useful form to do some work. That was the original concept. Let's move on. There's too many concepts I can try and go over. So exergy is the maximum theoretical work, meaning theoretical, it's on paper, you're never going to get that high. It's like the frictionless pulley. All pulleys have some friction, but it's the maximum theoretical work obtainable from a system and its surroundings. That is an and. So you say the system and its surroundings, and you're trying to get out of that system the maximum theoretical work. As the system undergoes a theoretical process, it's again a hypothetical process, you think it's going to have a lot of irreversibilities, or if it's going to be pretty reversible? It's going to be pretty reversible if I want the maximum work out. Like no irreversibilities. And when it starts from its current state, and then it's going to finally end up when it comes into equilibrium with its environment. Again, when you get to its equilibrium with its environment, it's dead. You can't make any more. So when the system is in thermal and mechanical equilibrium with the environment, it's not capable of producing any more useful work. It's said to be at the dead state. What is our typical dead state pressure? The pressure of the air in this room. What is our typical dead state temperature? Well, kind of the average surface temperature throughout the world, throughout the year, around 25 degrees C, 298 Kelvin. That's your dead state temperature and pressure. So when a system is in equilibrium, the temperature of the system is equal to the dead state temperature, and the pressure of the system is equal to the dead state pressure. Now, there's a subscript on this temperature. It's T0. Sometimes it's T, let me do this. Sometimes it's T like this. Sometimes it's T like this. I know it's hard to distinguish, but if you very focus on that subscript, what does that subscript look like? Does it look like a letter or a number? A number. And the number is 0. Is 0 a number? Yeah. 0, 1, 2, 3, 4. Sure. 0 is a number. Okay. So every now and then I'll put this. What does that look like? The letter 0, lowercase. So actually, if you really look at this textbook closely, you flip a few pages, you'll say, is that subscript the number 0, or the letter lowercase o, or the letter uppercase O? And I don't think it'll be completely consistent throughout our textbook. Does that mean you overpaid for your textbook? No, it just means there's flaws in textbooks, okay? But take a look at it, okay? And ask yourself that question when you look at it. It really, I like to think of it as a 0, 1, 2. It's like the dead state. And how do we number our states? Don't we have like state 1, state 2? State number 0 is the dead state. So most of the time, it's the number 0. Exergy is a measure of the quality of the energy. I could have a lot of energy, but if I can't convert it to something I want, it's not that useful. So you'll see that it's described as the quality of that energy. All right. Exergy is a property of the system, and it depends on the properties of the system. What is this P? Just as a little review. P. Pressure. It's the pressure of the system. The system could start out at 5 atm. What's T? Temperature. It could start out 300 Kelvin, 300 degrees C. It could start out at some high temperature, low temperature. What is V? The volume of the system. What is U? Internal energy of the system. They didn't list H, they skipped H. But what's the next property in our favorite list? S for entropy of the system. Then we have Ke and Pe. What is Ke of our system? It's the kinetic energy of the system. And what is Pe? Gravitational potential energy of our system. Okay. It also is not only a property of all of these of the system, it's a property of other properties of the environment. What is P naught, T naught? We just talked about it. When you put a subscript on that P, it doesn't mean the pressure of the system. It means the pressure of the environment, the local environment around that system, which is typically 1 atm. How about T naught? Same thing. It's the temperature of the environment. And it's also, so it's like 1, 2, 3, get those concepts down. For 3, it's a property of the system if it is in thermal and mechanical equilibrium with the environment. That is the hard part right there. What do you mean, Professor? I remember we take the system from its current state. We say, how much exergy do you have? Well, that exergy will be the maximum theoretical work obtainable from the system if I take it and put it through a process such that the dead state, it ends at the dead state. It's in thermal and mechanical equilibrium with the environment. During that process, I get the maximum theoretical work out. That's the exergy of the system. So when you see this V naught, is that the volume of the environment? Or is it the volume of the system in equilibrium with the environment? You see that? You got two choices. Is it the volume of the environment? Wrong. Or the volume of the system in equilibrium with the environment? It's the volume of the system in equilibrium with the environment. Likewise, U naught and S naught. So you start with the system, you go to the dead state. It's now at those theoretical dead state conditions, and that would be, here's the equation for the exergy. It's the current internal energy of the system minus the internal energy of the system at the dead state. It's the dead state pressure times the volume of the system starting initially minus the volume at the dead state minus the temperature of the dead state temperature. This is the entropy of the system minus the entropy of the system if it's in equilibrium with the environment. And then you have the kinetic and potential energy. All right. It looks like a bunch of pluses, but right there is a minus. It's a subtraction. So that's not a typo. It's a real a negative sign in front of that T. All right. Let's talk about this. What about this temperature and this pressure? Somebody said, oh, it's 25 degrees C. Are you going to put 25 degrees C in there? Or are you going to put in 298 Kelvin? Or does it make a difference? First of all, does it make a difference? Yeah, it does, right? And from your experience in Thermo 1, what do you think? You better put it in absolute temperature. How about this pressure? Is this gauge pressure or absolute pressure? We said it's 1 atm. I said it's the pressure of the air in this room. Do you feel a lot of pressure of the air in this room? No. So we would say the air pressure in this room is 0 gauge, but it's 1 atm absolute. It needs to be an absolute. This needs to be the absolute. This is correct. This is incorrect. All right. Also look at the units on entropy. What were the SI units on entropy? Kilojoules per degree C? No. They were always per Kelvin. Okay? All right. You want to see that derived? First of all, it's in the textbook. You can find the derivation in the textbook. But let me give you the fast derivation of the textbook. And what you're going to do is you're going to jump between first law and second law, using it first law now, then the second law, and let's combine them. And you're going to be jumping between, let's focus on our system only, or let's do the first law for the environment only, or the second law for the environment only. So it's like sometimes we're going to focus on the system. Sometimes we focus on the environment surrounding the system. Sometimes we do the first law for the system, first law for the environment, first law for the combined system, which is system and environment. Sometimes we do the second law. See what you're doing? So you're just going to be judicious in, okay, now let's use this one. So let's jump through it. First, you do an energy balance, which is the first law of thermodynamics. For the combined system, that's the system and the environment around it. And so you write the first law. Does that look like a good first law? Closed system undergoing a process. And then what do we say? We say over here to the rest of the world, to the rest of the universe, there's no heat transfer out of the combined system or into the combined system, so that's equal to 0. And so the work coming out of the combined system, that's really what we want, is negative of the change of the energy of the combined system. Not too complex, but then we say, well, what is the change in the energy of the combined system? Well, it's the change in energy of the system plus the change in the energy of the environment surrounding the system. And then you say, just by definition, that's change in U, change in KE, change in PE for both of them. And then you look and you say, the environment is just some massive blob sitting there. It has no kinetic energy. So the kinetic energy of the environment is 0, potential energy of the environment is 0. But now I've got the change in internal energy of the environment. I have to work on that. And I have the change in internal energy of the system, which is a little funny because we're ending at the dead state. So you start initial state, end at the dead state. State 2, the final state in a process, usually go from state 1 to state 2, is the dead state, so we put U 0. So that looks really funny. It's like, is there a typo here? No. Okay. Now, we go to the first law of the environment only. True? Does this look like a good first law of environment only? So we have the sum of the heat transfers from the system to the environment. That's the only way you can have a heat transfer to the environment. Remember, there's no heat transfer from the environment to the rest of the world, the universe. So the only way is between them. And then you have the work. There's no expansion work of the environment to the rest of the world. It's only this shaft work, this useful work coming out of the combined system. But it's coming out so that this work right here is really only this pushing of the system as the system expands into the environment. Or it could be a negative if the system contracts from the environment. So if there's a heat transfer into the environment, it came out of, look at the negative sign, the system. If there's a work transfer and it's only a boundary work between the system and the environment, then if you push if there's a volume change, like the volume of the environment expands, then the system has to be the same amount go down. So there's a relation in the volume change between the system and the environment. So you convert this boundary work of integral P dV to minus P naught V naught minus V. Notice that you start from state 1 and end at the dead state, which is a little tricky on the subscripts. So we now have, from the first law, the change in the internal energy of the environment is equal to this. Doesn't that look good? You go to the second law for the environment only. Does this look like a good second law for the environment undergoing a process? You have the change in the entropy. It can be increased by heat transfer coming in. Any irreversibilities generate entropy. We want to isolate this term right here. So you have a negative del Q. You put that in, switch it to the other side, multiplied by T naught, because T naught is a constant. It's not changing during the process. Just like P naught's not changing during the process. And now you substitute this one, del Q, in for right here. And you combine these two. And you get the change in internal energy. It's ready now to be substituted in. Combining first and second law, there's the group of terms. This is a derivation. Let me continue on. So now we substitute into our equation. We have the second law for the combined system. Did I describe what we're doing? First law, second law, let's focus on the system, let's focus on the environment, let's focus on the combined system. So here we have the change in entropy of the combined system. There's no heat transfer out of the combined system. You have some irreversibilities possibly. So we multiply by T0, you're ready to substitute here so that you could get rid of to get the change in the energy of the combined system. Let me look at this a minute. Right here. T0. Oh, for the entropy change of the environment. You then see that what we have is the work out of the combined environment is the negative of the change of the energy of the combined system. So the work out of the combined environment is equal to all of these properties, and it'll be less if there are some irreversibilities. And if there are no irreversibilities, then you'll get the maximum work out because it's only a negative absolute temperature times a positive entropy generation. So this is the maximum work out theoretical. Hence, you define or coin, or people have done it before, they said, look at this. This is a new thermodynamic property. We'll give it the name Exergy, and we have an interpretation for the Exergy. It's the maximum theoretical work out. Looks like we are at the end of our first lecture. Please ask me any questions after the class ends. Pick up a syllabi, pick up an equation sheet, and I'll see you Wednesday.